So, let us now see how we apply a finite difference technique for solving a linear boundary value problem governed by Dirichlet boundary conditions. Let us take the following example. So, we have a second order equation minus y double prime plus pi square y equal to 2 pi square into sin pi x in the interval 0 to 1, and there are Dirichlet boundary conditions which are specified at the end points 0 and 1 of this interval 0 to 1. So, y of 0 is 0 and y at 1 is 1. So, we observe that p of x is 0 and q of x is pi square, and r of x is 2 pi square into sin pi x with a negative sign. And since p of x is 0 and q of x is positive on the interval 0 to 1, we are guaranteed of a unique solution to the finite difference equation for any value of h. This we had already established. H must satisfy the condition that h is less than 2 by L. What is L? Modulus of p of x must be less than or equal to L for x in the interval a b. So, since p of x is 0 in this case, we are guaranteed of a unique solution to this finite difference equation for any value of x. So, we start applying all the steps that we had discussed for the general second order differential equation governed by the boundary conditions. So, in that step 1 is to partition the interval 0 to 1. So, let us divide this interval into 4 equal subintervals of width h, which is 1 minus 0 by 4, by means of points x 0, x 1, x 2, x 3, x 4, such that x 0 is 0, x 1 is 1 by 4, x 2 will be half, x 3 is 3 by 4 and x 4 will be 1. What do we have to do next? We will have to evaluate the differential equation at each of the interior points, namely x 1, x 2, x 3. So, it is minus y double prime at I plus pi square y at I, that is equal to 2 pi square into sin pi xi for I is equal to 1, 2, 3. What is the next step? We should replace the derivatives that appear in the differential equation by appropriate finite difference scheme. So, let us again replace the second order derivative in the differential equation by a second order accurate central difference scheme. If we do that, then we get minus yi minus 1 plus twice yi minus yi plus 1 by h square, h is 1 by 4, plus order of h square, because the error in this approximation is of order of h square, plus pi square into yi, and that is equal to 2 pi square into sin I pi by 4 for I is equal to 1, 2, 3. What should we do then? Next step is to drop this truncation error terms and replace each of the exact solution yi at these interior points by the corresponding approximate solution wi. So, when we do that, we get minus wi minus 1 plus this coefficient into wi minus wi minus 1, and that is equal to the right hand side. I is equal to 1, 2, 3, and this equation has been obtained after multiplication by h square, which is 1 by 4 the whole square. Now, we look at the boundary conditions. The boundary conditions are that y of 0 is 0 and therefore, w0 is 0 and y at 4 is 0 and hence w4 will be 0. So, we obtain the system AW equal to B as follows. So, we take W0 equal to 0 as the first equation. The next 3 equations are obtained by applying this at I is equal to 1, 2, 3, and our last equation is given by W4 is equal to 0. So, we combine all these, namely I have I equal to 0 equation given by this. For I equal to 1, 2, 3, my equations will be obtained from here, and finally when I is equal to 4, I have my equation given by W4 equal to 0. So, I take my unknown vector as a 5 cross 1 vector which has components W0 to W4, and I write down the system AW equal to B with coefficient matrix A to be a 5 cross 5 matrix. So, the equations are expressed here. Corresponding to W0 equal to 0, how do I express this? So, 1 into W0 plus 0 into W1 plus 0 into W2 plus 0 into W3 plus 0 into W4 is equal to the right hand side B, and W0 is equal to 0. So, B0 will be equal to 0. So, I apply these equations one by one and write the system AW equal to B, and we solve this system with the right hand side vector B given by this, and we observe that the solution vector W is given by this, which tells us W0 is 0, W1 which is an approximate solution at x1 which is 1 by 4, namely y at 1 by 4 is approximated by W at 1 by 4, and that is given by this. Y at half is this, and that gives you an approximation, namely 1.02530, and so on. So, the solutions at the interior points which are approximations to the exact solutions y at the interior points are given by these. And we note that the exact solution of the differential equation is given by y of x is equal to sin pi x. So, it is natural to see whether the solution, approximate solution that we have obtained by taking the step size h to be 1 by 4 is reasonably a good approximation to the exact solution of the problem. So, we list the exact solution at each of the xi and compare it with the approximate solution at the corresponding xi given by wi. So, we have a table of values where the xi's are specified, namely 0, 1 by 4, half, 3 by 4 and 1, at which the approximate solution and the exact solutions are written down, and we compute the absolute error, namely mod yi minus wi, the exact minus the approximate solution. And this column tells us that the accuracy of the approximate solution is quite reasonable in spite of the fact that the step size h is, which is taken to be 1 by 4, is not very small. So, we know that this system possesses a unique solution for any value of h, because the conditions that we had stated earlier were satisfied, which are sufficient conditions, and therefore, the solution possesses a unique solution, and we had taken h to be equal to 1 by 4, and we observe that our approximate solution is such that it is a reasonably accurate solution. It compares very well with the exact solution for this problem. So, we have illustrated the finite difference method of solving a boundary value problem governed by the second order equations subject to Dirichlet type of boundary conditions. What happens to the maximum absolute error in the approximate solution as a function of the number of subintervals? So, when I take n to be 4, my h is 1 by 4. So, I would like to increase the number of subintervals, namely double the number of subintervals, say 8. In this case, h will be halved, namely h will be 1 by 8. and I continue to double the number of subintervals into which I divide the interval 0 to 1. By doing this, every time the step size h is halved. So, I would like to now see what is the maximum absolute error and the corresponding error ratio. Namely, when I take 8 subintervals, this is the maximum absolute error, and when I take 4 subintervals, this is the maximum absolute error. So, what is the ratio of this to this? And I would like to compute the error ratios by doubling the number of subintervals each time. So, let us just look at this table and focus our attention on this column, namely the column which specifies the error ratio. So, the table actually presents a numerical verification of the second order accuracy of the finite difference scheme that we have used in the solution of the linear boundary value problem with Dirichlet boundary conditions. So, we observe that as n is doubled, h is halved, and the approximation error is reduced roughly by a factor of 4. Let us just see the error ratio. So, we observe that each time when n is doubled and h is halved, this approximation error is roughly 4 times reduced. That is what happens throughout. What does it indicate? It indicates that we have used a second order accurate different scheme to replace the derivatives which appear in the differential equation, and this is reflected in the fact that the approximation error is reduced by a factor 4. And so, the table clearly shows the numerical verification of the second order accuracy of the finite difference scheme that we have used in solving this boundary value problem with Dirichlet boundary conditions. So, it is another example which is again a boundary value problem governed by second order differential equations. Let us again solve this problem subject to Dirichlet boundary conditions. So, the differential equation is given here and the interval of interest is 0 to 1, and it is a linear boundary value problem, and the conditions are y of 0 is minus 1 and y of 1 is 0. So, the unknown function is specified at the end points of the interval. So, they correspond to Dirichlet type of boundary conditions. Now, let us find out what are p of x, q of x in this differential equation. P of x is minus of x plus 1, p of x is minus of x plus 1, q of x is 2, which is positive, and we observe that maximum of modulus of p of x for x in this interval is 2. So, this gives us L. So, what should we choose our step size h as? It should be less than 2 by L. L here is 2. So, take our step size h to be less than 2 by 2, that is less than 1. So, we are guaranteed of a unique solution of the finite difference equation for any value of h which is less than 1. What is it that we should do to solve this system? Step 1 is to partition the interval 0 to 1 into 4 equal subintervals. So, step size would be 1 by 4. So, what are these points? The points are x0, x1, x2, x3, x4, of which x1, x2, x3 are interior points, x0 and x4 are boundary grid points. So, we replace the derivatives which appear in the differential equation by appropriate second order accurate central difference formula, multiply throughout by minus h square, and then collect the like terms and then obtain the finite difference equation which is given by this. So, this is valid for I is equal to 1, 2, 3, which are the interior points. What are Pi? Pi are given by minus of xi plus 1. What is xi? Xi is x naught plus IH. X naught is 0, h is 1 by 4. So, xi is I by 4. So, minus of xi plus 1 is minus of 1 plus I by 4. What about q? Q of x is 2. So, q of xi, that is qi, is 2. What about r of x? It is 1 minus x square into e power minus x. So, ri is 1 minus xi square into e power minus xi, and we know xi is I by 4. So, we have substituted for xi as I by 4, and we have ri to be given by this. What other information do we have? We have w naught to be minus 1 and w4 to be 0. So, we now can write down the algebraic system of equations in matrix form, namely AW equal to B. So, the first equation, the W naught equal to minus 1, is given by the first equation here, 1 into W naught plus 0 into W1 plus 0 into W2 etc. is minus 1. Then at the interior points, we have the finite difference equation. From there, we write down these three equations. The last equation tells us that Wn is 0. What is Wn? That is W4. And so, W4 is 0, and that is what is expressed here in the last row of this system. So, we solve this system and obtain the solution vector W as this, which gives us the approximate solution at the interior points 1 by 4, half and 3 by 4, which approximate the exact solution y at these points, and the solution is given by this. We also know that the exact solution of the system is y of x is equal to x minus 1 into e power minus x. So, we would like to find out what the absolute error is. So, in the table we present the xi values, the corresponding exact solution at these xi and the approximate solution at these xi, and compute the absolute error. And we observe that the approximate solution compares very well with the exact solution, since the absolute error is very small. So, again we see that the approximate solution matches well with the exact solution in this case, and the conditions that we have imposed on P of x and Q of x are satisfied, and they are sufficient to ensure that the system has a unique solution, and this approximate solution compares well with the exact solution. So, we have discussed how to solve a linear boundary value problem subject to Dirichlet boundary conditions by using a finite difference method. The steps involved are such that we replace the derivatives by a finite difference approximation and arrive at a system of algebraic equations, and the solution of this system gives us the approximate solution at the interior points, which are obtained by dividing the interval into n equal subintervals. And we also have determined the conditions under which this Dirichlet boundary value problem, which is converted into a system of algebraic equations, possess a unique solution. So, we take care to choose the step size h in such a way that the conditions specified are satisfied, then we are guaranteed with a unique solution for the system AW equal to B, and we will be able to obtain the approximate solution to this boundary value problem by finite difference method at the interior points at which we seek this solution. Now, the question comes, what do we have to do if we have a boundary value problem which is governed by boundary conditions which are not of the Dirichlet type. Namely, the boundary conditions are either of the Robin type or of the Neumann type. So, we shall discuss the details now. The procedure is analogous to what we have done for the Dirichlet problem, with slight modifications, namely the boundary conditions are of the Robin type or the Neumann type. So, we have to make some modifications to write down these boundary conditions and incorporate them into the algebraic system. So, let us see how this can be done. We now consider linear boundary value problem with non-Dirichlet boundary conditions. Consider the one-dimensional 2-point boundary value problem. It is a linear boundary value problem. So, the differential equation is y double prime equal to p of x y prime plus q of x into y plus r of x for x in the interval a b, and the boundary conditions are of the Robin type. We impose the condition that alpha 2 is different from 0 and beta 2 is different from 0, because we are now interested in boundary value problem with non-Dirichlet boundary conditions. So, as before, we partition the interval a b into n equal subintervals by points x 0, x 1, etc., x n minus 1, x n, where the step size h is b minus a by n. So, the points x I are given by x 0 plus I h for I is equal to 0 to n. So, as before, let w I denote the approximation to the exact solution y of x at x is equal to x I. So, there are n plus 1 unknowns w 0, w 1, etc., w n. So, we require n plus 1 equations to solve for these n plus 1 unknowns, out of which n minus 1 equations can be obtained as before by replacing the derivatives which appear in the differential equation by means of appropriate finite difference approximations and using the resulting finite difference equation at the interior points I is equal to 1, 2, 3 up to n minus 1. So, if we do that, then we end up with this equation which is valid for I is equal to 1 to n minus 1. This is exactly obtained in the same way as we had done in the previous case, where we have explained the method of solution of boundary value problem with Dirichlet boundary conditions. Now, we have to apply the boundary conditions and see what we get from the boundary conditions. Let us look at the boundary conditions. They are either of the Robin type or they are of the Neumann type. So, we deal with the boundary conditions as follows. Namely, when we are given the boundary condition at the left end point, namely x 0, which is a, we introduce a fictitious node x f to the left of x 0 such that x 0 minus x f is h, the step size that we have already taken. I repeat, when we want to apply the boundary condition at the point x 0 and get the corresponding equation which should be incorporated in the algebraic system, we take a fictitious point x f to the left of x 0 at a distance of h units from x 0 and call the approximate solution at that point as w f. And I apply at x is equal to x 0 what happens to the finite difference equation. We see that the finite difference equation turns out to be this. When I take I is equal to 0 in the equation that I had shown. This involves WF. Do I know WF? Yes, the first boundary condition which is prescribed at the left end point A will help me to find out what WF is. Let us see how it is obtained. What is the boundary condition? Alpha 1 into y of A plus alpha 2 y prime A is alpha 3. So, this is alpha 1 into y of A is y at x naught, and an approximation is w naught. So, alpha 1 into w naught plus alpha 2 into, we need to replace the derivative y prime at x naught. What is y prime at x naught? We replace it by a second order accurate finite difference method. What will that be? That is going to be W1 minus WF by 2H. Let us see how we have obtained. So, we want to apply the finite second order finite difference approximation to the first derivative at this point x naught. So, y prime at x naught is equal to the value of y at this point minus the value of y at this point xf divided by the distance between the 2 points, namely 2h, and that is what we have written here. So, y prime at A is replaced by W1 minus WF by 2h, and the boundary conditions tells us that this is equal to alpha 3. And from here we can obtain what WF is. So, WF will be W1 minus 2h by alpha 2 into alpha 3 minus alpha 1 W naught. Of course, W naught, W1 are unknowns. So, WF is also an unknown that appears in the differential equation, and since xf is a fictitious point, I am not interested in obtaining the solution there. So, I express the solution at xf in terms of the solution at the other points at which I seek the solution. So, at x is equal to x naught equal to A, the equation that I should use is this, which is obtained by substituting for WF in this equation. So, this is going to be the equation that I should use at x is equal to x naught, which is A. Now, this equation has been obtained when we have a Robin boundary condition. Let us consider the special case. When we have alpha 1 to be equal to 0, then our boundary condition turns out to be alpha 2 y prime A is alpha 3. So, y prime at A is alpha 3 by alpha 2, which I denote by alpha. So, y prime at A is alpha, and therefore, that corresponds to a Neumann boundary condition, because the derivative alone is specified at one end point A. So, in that case I can deduce the equation that I should use from here by substituting alpha 1 is equal to 0 in this. So, that gives you the equation as this. So, if a Neumann boundary condition is specified as the first boundary condition, then the finite difference equation that should be used and should be incorporated in the algebraic system is given by this. So, I repeat, if it is a Robin boundary condition, this will be used in the algebraic system as the first equation. If Neumann boundary condition is specified as the first boundary condition at the end point A, this equation will be used as the first equation in the algebraic system. And from second to n minus 2 equations are obtained from the differential equation by replacing the derivatives by appropriate finite difference approximations and so on. And what happens when the boundary condition which is specified at the other end point, namely B, is of the Robin type? namely beta 1 into y of b plus beta 2 into y prime at b is equal to beta 3. In this case again, this y prime b will have to be replaced by a second order accurate central difference formula. That would require an additional point to the right of b. So, we introduce a fictitious point. B is our xn. So, the fictitious point which appears on the right hand side is going to be xn plus 1, such that xn plus 1 minus xn is h. So, the derivative at xn is going to be value at xn plus 1 minus value at xn minus 1 divided by 2h. So, it is going to be y prime at b will be replaced by w n plus 1 minus w n minus 1 divided by 2h. So, replacing y prime b in that way, the equation that should be incorporated as the last equation in the algebraic system will be obtained by substituting for w n plus 1 obtained from this boundary condition. So, we have the following system when we complete doing all this, which when solved will give us an approximate solution. So, let us consider an example to illustrate how we can solve the boundary value problem for non-Dirichlet boundary conditions. We now consider an example to illustrate the method of solving boundary value problem governed by differential equations of second order with non-Dirichlet boundary conditions. So, the given differential equation is y double prime plus y equal to sin 3x in the interval 0 to pi by 2. The first boundary condition is of the Robin type, y of 0 plus y prime 0 is minus 1, and second boundary condition is a Neumann boundary condition, y prime at pi by 2 is 1. So, we partition the interval 0 to pi by 2 into 4 equal subintervals of width h, which is pi by 2 minus 0 by 4, which is pi by 8. So, our xi will be I pi by 8 because x naught is 0 and I will vary from 0 to 4. Let us find out what are y of p of x and q of x and r of x. P of x is 0 and q of x is minus 1 and r of x is sin 3x. So, for each I, pi is 0, qi is minus 1 and ri is sin 3I pi by 8 for I is equal to 0 to 4. And we also note that alpha 1 and alpha 2 take the value 1, alpha 3 is minus 1 and beta is 1 because the second boundary condition is a Neumann type of boundary condition. So, we obtain now the system of finite difference equations in matrix form. What do? We replace the derivatives in the system by appropriate finite difference methods. So, we would like to replace them by second order accurate finite difference formulas in this problem, and then evaluate the differential equation at the interior points and obtain the resulting equations for the unknowns which are approximations to the exact solutions of the differential equation. Namely, the unknowns are wi. When we do all this, we end up with this equation, namely wi plus 1 minus 2 wi plus wi minus 1 by h square plus wi is sin 3 xi for I is equal to 1, 2, 3 at the interior points. Now, the first boundary condition is the Robin boundary condition, and therefore, we have to replace the derivative there by means of a second order accurate central difference scheme. When we do that, we get Wf, which is the approximate value of y at xf, where xf is a fictitious point introduced to the left of x naught. So, Wf turns out to be this, and it is expressed in terms of W naught and W1. So, this is obtained from the first boundary condition, which is of the Robin type. The second boundary condition is a Neumann type of boundary condition, and therefore, we replace the derivative there by means of the second order accurate finite difference approximation. So, y prime at the end point pi by 2 is specified to be 1. So, we introduce a fictitious point x n plus 1 to the right of x n and replace the derivative at x n by the value at this point minus the value at the left point, which is x n minus 1, divided by the distance between the 2 points, which is 2h, and that is what we have done here. W n plus 1 minus W n minus 1 by 2h is 1. This is the approximation that we get when we replace the first derivative at the end point, namely x n is equal to pi by 2. From here we get what W n plus 1 is, which is the approximate solution value at the fictitious point which we have introduced, namely x n plus 1. So, all the equations that have to be incorporated into the system are available with us now. So, we write down the system A w equal to B as this, as the coefficient matrix, and W has components W naught to W 4, and vector B is given by this. In this coefficient matrix, we have D, which is given by 2 minus pi by 8 the whole square. So, we solve this system and obtain the solution vector as this. So, we have been able to use finite difference method to obtain approximate solutions to the boundary value problem, where non-Dirichlet type of boundary conditions are specified, namely Robin type of boundary conditions and Neumann type of boundary conditions are specified. So, we would like to now see whether we can obtain the absolute error and check whether our approximate solution to this problem is reasonably good. So, let us find what the exact solution is. We observe that the exact solution is given by y of x is equal to minus cos x plus 3 by 8 sin x minus 1 by 8 into sin 3x. So, we write down in this table the xi values, the corresponding approximate solutions that we have obtained using finite difference method, the exact solution, and then compute what the absolute error is at each of these xi. And we observe, looking at the column in which the absolute error, which is the difference between the exact solution and the approximate solution at each of the xi, we observe that the approximate solution agrees quite well with the exact solution, since the absolute error is small. So, the accuracy of the approximate solution is quite reasonable, in spite of the fact that the step size h chosen by us, namely pi by 8, is not very small. In addition, we would like to check the numerical accuracy of the second order scheme that we have used to solve this boundary value problem. So, what do we do in order to assess this? We increase the number of sub intervals into which we have partitioned the interval 0 to pi by 2. we used 4 subintervals in our computations earlier and obtained the approximate solution. So, we doubled this number of subintervals, namely we divide the interval 0 to pi by 2 into 8 equal subintervals of step size pi by 2 by 8, so that pi by 16 is h. So, h is halved as a result of doubling the number of subintervals, and we continue to do this, and in each of these cases we list down what the maximum absolute error is and see what the error ratio is, namely the ratio with n is equal to 8 by n is equal to 4 of the maximum absolute error that we have obtained. We observe that the error is roughly reduced by a factor 4 when we double the number of subintervals, say from 4 to 8, which clearly indicates the numerical accuracy of the second order finite difference scheme that we have used in solving this boundary value problem by a finite difference method. So, this happens each time we double the number of subintervals, in which case the step size h is halved. So, h becomes smaller and smaller, and we observe that the error ratio in this case is close to 4, showing that our approximate solution is very close to the exact solution, and the second order scheme that we have used has helped us to obtain solution which are very close to the exact solution. So, in this lecture we have discussed finite difference methods of solving linear boundary value problems, which are governed by second order differential equation subject to either Dirichlet type of boundary conditions or Neumann type of boundary conditions or Robin type of boundary conditions. So, we close our discussions on the finite difference techniques of solving boundary value problems, and in the next class we shall consider another technique which is known as a shooting technique for solution of boundary value problems, which are linear boundary value problems.